significantly reduce the amount of material we are losing by generating one wafer. Calculations show that we can generate up to 2 times more wafers out of a given crystal compared to the mechanical soldering process.
This is the podcast for engineers, the podcast you just have to listen to if you're interested in what's going on in the semiconductor market. Today, I'm here with Dr. Peter Friedrichs. Peter, why don't you introduce yourself?
Yeah, thanks, Cassie. My name is Peter Friedrichs. I'm for a long time already with Infineon dedicated to Silicon Carbide. So that's my passion. That's my professional background. I had various roles in development, but also other functions. And I'm very happy to be here and to talk with you today about some specific aspects of this new technology.
Well, we're very happy to have you. So for anyone following along who listens, probably knows that Infineon is really focused on decarbonization and digitalization. One of the major aspects of decarbonization is getting more out of less, so producing less waste. Do we have any technologies, perhaps, that help us really get more out of less?
Yeah, absolutely. So definitely Silicon Carbide belongs to those technologies in various dimensions. Of course, our products help to reduce waste of energy, to reduce material consumption when building complete power electronic systems. But we go one step further. So we also look back into the whole value chain, production chain of the devices itself. And here, especially in the case of Silicon Carbide, the material itself, which is basically the baseline to produce those powerful chips, comes along with a pretty demanding technology flow to grow the crystals. And of course, also here it is very important that the material we grow with a lot of energy and time is used as best as possible, meaning we also would like to avoid any waste on the production side of the material itself.
So I've heard of a new technology called cold split technology. Can you tell us a little bit more about this and how it relates to silicon carbide?
Right, yeah. Cold split technology is a fascinating new approach how to generate the so-called wafers, basically the disks we are using to produce chips, out of the grown crystals. Traditionally, the technology to generate those wafers is a mechanical soldering process, which
using wire saws, right?
Wire saws, for instance, yes, which by nature creates waste simply due to the abrasive process. So
it's creating dust, or
exactly. Yeah. It's more or less a dust you generate, and and simply you discard very valuable material which you have grown in a very demanding process before. And a cold split is a technology which avoids basically this creation of dust due to an abrasive process. So cold split was originally developed by a company called Silicon based on some innovations generated at Harvard University and later being transferred to Silicon in Dresden in Germany. And the guys in Dresden developed this technology into a stage where it really became very interesting, especially for Silicon Carbide. And for that reason, Infineon acquired this Silicon startup in 2018. From that point onwards, we were working on the commercialization of the cold split principle for the generation of silicon carbide wafers.
Okay, so Silicon had the idea of cold split, and now we're working with them to really make it a practical solution to implement into the production line, right?
Exactly, yeah. So as typically for startups, so they are very innovative. They work on a basic principle and improve it into an, let's say, pre-production stage. And that's the point in time where we stepped in saying, okay, we have the proof of concept, but now we need to turn it into a productive process. And of course, we have the challenge that the technology itself is still very young. It still improves and develops further. So we have now a mixed setup where we, on the one hand side, use this technology productive, but in parallel, we further improve and further develop, of course, this cold split technology into next generations. So.
Can you tell me a little bit about how cold split technology works compared to wire sawing? What is it step by step? We start with a boule. I
Exactly.
assume.
So the starting point is the same like for wire sawing. So we grow a crystal, we shape it into a mechanical outline which corresponds basically to the later wafer. What we now have to do is it's basically a relatively thick piece, and we have to cut it into individual wafers. So the typical standard thickness in silicon carbide is a bit less than half a millimeter, exactly 350 micrometer. And those discs we would like to generate out of a piece of silicon carbide which is a few centimeters thick. Wire sawing is mentioned, so it simply does how the saw works, as we all know it from home maybe. Cold split has a different approach. So with cold split, we try to separate the material without losing any material. How we can do that? And actually, we do two steps. First step is define the depths in this crystal where we want to separate or generate the wafer of, meaning in the case of a 350 micrometer wafer, we go down to about 400 micrometer roughly. We define and let's say something like a perforation, so a pre-damaged layer, which is still not a complete separation, but it's basically a predefined damage layer.
Okay,
This
like
we
on
do
a
by-
piece of notebook paper, you know,
Exactly,
to
yeah.
help you rip it off.
Correct. And how to do that? Simply we use laser technology, which we can focus in a particular depth, and we generate a very specific damage layer. Next step is we need to apply a certain force to do the actual separation. And this is, in case of cold split, generated by a polymer process. So we have a polymer layer, a soft polymer, which is laminated onto the front side of the already prepared boule. And if you then cool down the stack, so the crystal together with the polymer on top, the polymer contracts. So it simply it goes through its so-called glass point. It becomes really solid, and since the boule itself more or less remains like it is, so we create a very high force, and this force basically leads to a separation of the wafer from the edges exactly through the level we have predefined by the laser.
Okay, how cold does it have to get?
Actually, we are using liquid nitrogen, which is about minus 160 degrees C approximately.
Okay.
So that's the target temperature we are using to separate basically the two.
Okay, so it's basically like common physics. When something gets cold, it retracts.
It attracts, right. And we are using the fact that depending on the material properties, materials have different, let's say, contraction level. So as the polymer contracts heavily, so it really shrinks significantly, while the boule, of course, also contracts, but not by far not as strong as a polymer. And this difference basically is the trigger of a force which helps us to separate the wafers. So
Okay.
this we then do basically subsequently again and again. And since we just have this interface of separation, which we have to, let's say, prepare later on for the next step, so we can significantly reduce the amount of material we are losing by generating one wafer. So calculations show that we can generate up to 2 times more wafers out of a given crystal compared to the mechanical sawing process. That's
Okay, wow,
a significant benefit.
Definitely. So you use the same boule and you do the cold split process multiple times to just get to
Correct.
the total amount of wafers.
Correct, yeah.
Okay, great. That's fascinating and really a great proof point of how we're getting more from less, especially in silicon carbide, such a valuable material. What are the next steps? How can we make this commercially viable? How can we make this part of our current production process?
Yeah, the key task here is, since the technology is very new and all the equipment we are using is more or less homemade, so
Made specifically for this purpose,
specifically
right?
for this purpose, except a few minor tools, but the major tools are really dedicated to this process. So as a first step, what we had to do over the last years is to find partners to develop a tool park which is suitable for mass production, which is compatible with the typical setups we have in semiconductor manufacturing. So it means automation, handling options, monitoring, metrology tools, process control. So a lot of development and innovation was necessary. Where we are today, we are very happy to say that now we are able to ramp. So we have in the original site in Dresden already made a move into a larger facility where we have now a professional clean room environment with the already mentioned professional tools. We are productive with this material already since 2021. We are now ramping in the Dresden site in parallel to the R&D. Also, we have a production part there. But the major ramp we are currently starting in our Asia fab in Kulim. So also there we have basically a copy of the tool set we have developed in Dresden, now installed with an even higher level of automation. And of course, this is a fab running 24/7 with a very high efficiency. So therefore, we have this dual setup to roll out the technology, and within the next few years, we will also significantly then contribute to the total wafer supply we are having at Infineon.
Mm-hmm. So this, with cold split technology, it also gives us more of a handle, more influence on the entire life cycle of silicon carbide, right? Why is that important to us?
Yeah, the question of CO2 footprint of our products is something what customers are asking more and more in today's times, and all of them have in mind that silicon carbide is very energy intensive in the production, and therefore it's a clear measure for us to better understand on the one hand side the technology also for generating the crystals, but also delivering real facts how we can further improve the CO2 footprint. In fact, it's already shown today that silicon carbide delivers a better CO2 footprint than silicon, simply due to the fact that we have much smaller chips, but we want to do more. I think the community knows Infineon has a very ambitious target to be CO2 neutral already by 2030, so long before the European Union has set this target for itself. So therefore, it's a solid contribution. That's also one of the reasons why we want to be engaged here in the optimization of the material utilization. There are some minor additional technical aspects which come along with having this wafer generation process in our own hands. It's, for instance, the preparation of what we call the epi-ready surface. So it's very important for the next steps that we have here a well-controlled and high-quality surface stage available. So that's with cold split and the subsequent processing, of course, something we have in our hand and under our control.
Mm-hmm. Okay, well, thank you so much. I think this has been a really valuable conversation about cold split technology.
Thank you, Kelsey.
And if our listeners are interested in learning more or seeing actually the steps of the process, we do have a video on our website. We'll be sure to link it in the description. So if you're interested, please check out our Dresden facility where Semiconductor shows the step-by-step process of cold split technology. Thank you so much again, Peter.
Thank you, Kelsey.
So this has been the podcast for engineers. Thanks for listening, and be sure to stay tuned for more episodes on semiconductors and the technologies around them.